Hello and welcome to this tutorial. Today I will teach you the topic integration. In this lecture we will have a very basic understanding about this topic. But before that, let us have an overview of this topic. Integration lies under a broad concept called calculus, which has three main parts. First is limits, second is derivatives, and the third one about which we are talking today is integrals. This whole calculus was first discovered by Sir Isaac Newton while he was formulating his famous laws of motion and gravity. While he was studying these topics, he found out that the existing concepts and tools of mathematics were not advanced enough to help him with his derivations. So, he came up with some new mathematical tools called calculus. Now, let us see about why integration is so important. Let us take a simple function fx equals x square. We can also write it as y equals x square. Here is the graph of this function, which is an upward parabola. If we restrict the x-axis of this graph from x is equal to 0 to 5, then this graph will look like this. The area under this curve from x equals 0 to 5 is shown in red color here. If we try to approximate this area, we can do it by dividing this large interval 0 to 5 into smaller and equal intervals. Now let us assume that number of intervals that are formed finally are equal to n, and the length of each interval, which are obviously the equal intervals, is h. Draw the rectangles corresponding to each interval, taking the width of that rectangle equal to h, which is the length of that interval, and the height of that rectangle we can take as the value of the function corresponding to that particular interval. That value of the function we can take in totally three ways. The first case is when we take the smallest x value and take the value of the function for that whole interval corresponding to that lowest x value. The second case is when we will take the largest value of x and correspond the value of the function to that whole interval according to that value. In the third case, we can take the average of that small interval and find the value of the function for that middle value and allocate that value of the function for that particular interval. Now let us understand this in a little bit detail. We can take the value of h according to our assumptions. First of all, let us take the value of h, which is the width of rectangles, equal to 1. Taking that, we can make these graphs that are the graphs of areas. First of all, for the first case, this is the graph where we have taken the value of the function for each interval corresponding to its lowest x value. As in the small interval 0 to 1, we have taken the lowest value, that is 0, and we have allocated the value of the function for that whole interval 0 to 1. Same for the other intervals, as here in the interval 1 to 2, we have taken the value x is equal to 1, and for that whole interval, we have taken the value of the function corresponding to that x value, that is equal to 1. Similarly for other intervals also. In the second case, we have taken the largest value of x and we have corresponded the value of the function for that whole interval according to that. See here, as in the interval 0 to 1, we have taken the largest value, that is 1, equal to x, and corresponded the value of the function for x is equal to 1 for that whole interval. In the other cases also, as we take this example 3 to 4, in the interval 3 to 4, we have taken the value of the function for x is equal to 4, which is the largest value for that interval, and we have drawn a rectangle for representing the area. For the third case, we have taken the middle values for each interval. It is not looking very similar to this graph that we are approximating. It is nowhere close to that upper graph. Now let us take the value of h as 0.5. Now the width of each rectangle is 0.5 units of x. For that, we have made these rectangles representing the area under the curve for each of the three cases. Now look at these three graphs and compare it to these upper three graphs. These are looking somewhat closer to the approximation we are needing. Now we have decreased the value of x further. We have taken it 0.1. See how close it is to the approximation we are needing. Now take the smaller value of h further. We have taken h is equal to 0.01. See that the irregularities that was visible in the above graphs have also now vanished. From this all graphs, we can conclude that when we decrease the value of h further and further, then we can approximate the area under the curve very accurately. But here is some problem. For h is equal to 0.01, which is looking very accurate, when we have to calculate this area corresponding to the rectangles having very less width, then we have to add up the area of each rectangle. Now in this interval 0 to 5, in case of h is equal to 0.01, there are approximately 500 rectangles. Adding up the areas of these all rectangles manually is very difficult. Here is where calculus plays its role. Here is the importance of integration. Now let us come to the actual concept of integration. In integrals, we take this h, which is the width of that rectangles, as delta x, because it is the change in the value of x variable. Delta represents the change. Now for very small value of delta x, we can represent it as dx in calculus. Doing this, the rules of integration make it very easy to calculate that area of rectangles that we have made previously. This is the symbol of integration. One important thing you need to know is that integral is an operator. It itself does not have any meaning. We have to operate it to a function to realize its importance. As we were estimating the area under the curve of function x square with respect to the limits x is equal to 0 to 5, we can easily calculate that area under the curve calculating the value of this integral, where this 0 is the lower limit, 5 is the upper limit, and this is the function that we are needing, and this dx is the width of that thin rectangle. Okay, now we just have to calculate the value of this integral. There is no need to do that horrible calculation that we were seeing previously. Now let's see how to solve these types of integrals, these types of problems. Actually, integration is of two types. First is definite integration and the second is indefinite integration. Definite integration is the one which has some limits, and the indefinite integration does not have any limits. The answer of any definite integral gives us a specific value. It gives us the absolute area under the curve of the function of which we are calculating the integral corresponding to the given limits. The indefinite integrals do not give us a specific value. It gives us an expression plus an undeterminable constant as an answer. We can apply some limits to that indefinite integral and we can get a specific value as it was obtained in the definite integral. Now let us learn some simple rules of integration. If we are calculating the integration of a constant multiplied by a function dx, then we can take the constant outside of integration and the answer will be obtained as the constant multiplied by integration of that specific function. The second formula is if we have the integration of two different functions, then we can individually calculate the integration of that particular functions and add or subtract them according to the question. The third formula is if we have to calculate the integration of a polynomial function. We have x raised to some power, and then its integration will be equal to x power n plus 1 upon n plus 1 plus c, that is the undeterminable constant. Now the last formula that we will see in this video is integration of a function given some limits a to b. We can simply calculate the indefinite integral without the limits and apply the limits to that particular answer. If for a function small fx, the indefinite integral answer is capital F of something x, when we will apply the limits to that integral, then it will be capital F of the upper limit minus the capital F of the lower limit. Now let us solve the actual problem that we were seeing previously, that is integration of x squared dx with the limits 0 to 5. Now we can calculate the indefinite integral of x squared dx using this formula c. Integration of x power n dx is equal to x power n plus 1 upon n plus 1 plus constant. Now integration of x squared will be x power 2 plus 1, that is 3 upon 3. Now we can apply the limits that are given to this function, that are 0 to 5. This expression that we have obtained, we will put in the value of the upper limit in it, minus we will put in the value of the lower limit. So calculating this, we have obtained the actual answer to be 125 upon 3 square units. That is the area under the curve, that is this area here. Okay, so in this lecture we have studied the overview of calculus and integration. And we have seen the importance of integration. If we have to estimate the area under the curve of any function between the given limits, then we can approximate that by making the rectangles. But doing the calculation of that rectangles for such small values of h is very difficult. Using the formulas of integration, we can calculate that areas very easily that we have calculated here. So thank you so much.